Okay, so I have to also check. So last time we finished with Kelvin Helmholtz instability. And this time we will be continuing a little bit with instabilities because it is useful to know how these things are usually done. And also there is one more quite important in the case of instability. This is the Rayleigh-Taylor instability, which happens if you have a heavy liquid on top of a light liquid. But yeah, before we go, like last time, we just obtained the results, and then the time was over, so we didn't have too much opportunity to reflect what we have. And let me open the PDF from last time. From last time. And I copy the result of what we obtained into the whiteboard. So, Arthur, you okay? You are seeing everything fine and hearing everything fine. So, if yes, then please just type into the chat if you don't have.
So yeah, I can see everything fine. I have to eat my lunch. Sorry for that. So I thought it'd be nice to leave the camera off for that.
Doctor, type into chat if you can hear and see everything fine. Okay, good. Then let us continue. So here is the formula what we derived last time, and then I commented that if omega square is negative, then we have, let's suppose sigma equals 0, for instance. Then we have omega square equals to minus k square, and omega equals plus minus I gamma, where gamma equals k times u, so that all the perturbations start growing according to exponent e to the power of I omega equals e to the power of plus minus I goes to square, so it goes like actually goes minus plus, but it doesn't change much. A minus plus gamma times t. I omega t is minus plus minus gamma t. Now we have both plus and minus. What does it mean? It means that actually we have total solution will be like, let us say, amplitude of the perturbation x is going to be initial amplitude, first integration constant x1 e to the power of minus gamma t, and superposition of those two solutions x2 plus gamma t. And then we can see that one of them goes away as time goes on, and the other one remains and it starts magnifying. So overall, it will start growing exponentially in time. And that's what we call linear instability, is the perturbation grows in exponentially in time. And this is usually pretty much with all the instabilities when I can linearize this universal behavior. Now, actually, this is instability which you can also see, you probably have seen quite a plenty of times. Now, can you suggest when you have seen Kelvin-Helmholtz instabilities in nature? Can you? Well, I'm sure you have seen, but can you tell me where did you see? Yeah, one situation is clouds. How will the clouds look like when you have Rayleigh-Taylor instability?
I think they should look like kind of like ribs or.
Yeah, so like if you have maybe I can Google here some pictures for Rayleigh-Taylor instability. Again, the Helmholtz instability. It would be probably the best. Stability, and let us Google for pictures. Now, okay, here are now. I think I share the screen right now, so that Arthur can also see my screen, not just the whiteboard. Yeah. So if you Google for Kelvin-Helmholtz instability, then and image is flipped. Then here are like a linear stage of Kelvin-Helmholtz instability. I think this picture is quite good. Right? So we have a linear stage when you have sinusoidal perturbation, and then it evolves into a non-linear stage. Yeah, the picture is scheme here below. I think it's quite a good representation of what is going on. So we have two different wind speeds. Why do we have two different wind speeds? Well, that's because in upper atmosphere you have like zonal flows which are strong, and well, you all of course know that if you go to somewhere far away, like Far East or to states, then actually the time it takes for a plane to reach destination depends on the direction. Have you calculated how much you travel there and how long will you travel back? Have you compared? Usually there is quite a big difference. And also, furthermore, you usually see also as a map how the plane flies. Then there is also difference. The trajectories differ very much if it goes one way or the other way back. The reason is at the higher atmosphere there are strong zonal flows, like 100 kilometers per hour or more, and like these are like well in lower layers we have those merely quite moderate wind speeds. Then up in the upper atmosphere, wind speed is quite strong, and it's homogeneous, not so much differing depending on cyclones or anticyclones. Of course, it depends also, but to a lesser degree. And so there is like interface between upper layers and lower layers. And there is, that's why you have at the interface of those two flows, you will have Kelvin-Helmholtz instability like that. And what we you start with initial perturbation, which goes into a sinusoid, but then if the sinusoid grows, it ends at a non-linear stage. So what we did here, we linearized, but then you cannot linearize, and then you might have fancy structures like those here, like clouds in atmosphere. Okay, but now apart from that, where else have you seen Rayleigh-Taylor instability? Again, I am confusing. Rayleigh-Taylor is also very important, but right now I speak about Kelvin-Helmholtz. So where else have you seen Kelvin-Helmholtz instability? Just let me copy figures from here also to the screen, because this is what will be remaining for you. So where's? No one, no else? Just only in the atmosphere? What about water surface? You have been on seaside or wherever you have very cold water surface, which like mirror. And then wind comes. Then what happens? You have a ripple on water, and this is also caused by the same thing. Well, this is a little bit different in that here before we had we assume that we have two media with the same density, but in the case of water here we have one is high density water, and the other is 1,000 times less almost density, which is here. But still the same thing, that if you have shear, which means that one is at rest and the other is moving, you will be having still the same Kelvin-Helmholtz instability. But if we speak about water, then actually there is another thing. And the other thing right now here, when I wrote that omega square, we had only surface tension because we assumed densities are equal. But if you had assuming densities different, then you would be having here also the term corresponding to gravity effect, because surface is flat because gravity pushes it downwards. And then if the wind is not strong enough, then actually gravity can't stabilize. Like here in this formula, if U is small, then instability will not involve. Omega is real, which means that you have sinusoidal dependence and not exponential. If you have here gravity, then you have a similar term with plus sign in the right-hand side of that so-called dispersion relationship. So this is dispersion relationship. So a dispersion relationship which relates omega to k. So dispersion. And yeah, if you add here gravity effects, then you would be having something like additionally plus something like of the style density of rows, delta rho divided by average of rows, maybe, and then times g times k, something like that. Add it to everything. Now this got a little bit. We are deriving this expression also, but we'll be deriving it for different case. Let me undo and write it better. So here we would be having additional term. Oh. We'll be having here additional term plus something like row 1 minus row 2 divided by row 1 plus row 2 times g times k. Something in this style you would be having additional term. And because this is positive, well, actually it might be negative because row 1 minus row 2 might be both positive and negative. But if it is positive, then it can stabilize that u term over here. Because u is what makes the expression negative, making it unstable. But this is what makes it stable, and this makes it stable as long as it is positive. So if you have air flow or wind over a calm water surface, then you have also like a criticality that if the wind is weak enough, then no ripple will arise. You have like you don't need to have completely windless to have a mirror surface. But if it's above critical level, then ripple will appear. And then in long term, that ripple will evolve into water waves. Okay. Now, these instabilities are what make one contribution to turbulence, are basically responsible for the turbulence. As I mentioned, that turbulence evolves from shear is Rayleigh-Taylor instability at the boundary layer, like near walls or something like that. And then let us consider now the other instability, what we already mentioned, Rayleigh-Taylor instability. Now, let us recall how we derived the Kelvin-Helmholtz instability. We linearized, we obtained certain form of the perturbation, how water moves, and then we linearized equations, Navier-Stokes equation, and obtained equation related then the pressure above the interface and beneath the interface to obtain equation for linearized equation. So let me write also in general case, if you need to derive any type of instability, or also not necessarily instability, but dispersion relationships, to derive omega of k. And if omega becomes imaginary, then this means you have instability. So to derive omega of k, then the steps are write down your equations of motion. Like in this case, it is the Navier-Stokes, but in plasma you have different equations like magnetohydrodynamic equations, or well, you have different opportunities over there, like two fluid approximation. You have electron fluid and ion fluid, and then for both of them you can write equations which are similar to Navier-Stokes. And then you have also expression for electric field, and you have a lot of equations. It will be a lot more math than what we did right now here, but the basic remains the same. Write down your equations of motion. This is the first. Then second is linearized. And then at the end, of the day, you have like equation in partial derivatives. You have the partial derivative equations, partial differential equation, possibly a set of possibly many, possibly more than one. And then the third step is go to Fourier space. What it means that if you have derivative over x, you substitute this with I times k, and the derivative over time, you substitute with minus I omega. And then you had before a differential equation, now you have algebraic equation because derivatives got substituted with constants. And then fourth step is require that the determinant of this, so this will be equation for finding the amplitudes of these solutions. So you have PDE for certain physical quantities like displacement of the body. So now this is a set of algebraic equations for the amplitudes, not specifying what amplitudes, amplitudes. It might be displacement, it might be electric field, it might be potential, whatever it has. And then you should have, if everything goes well and you have forgotten anything, you should have as many equations as you have those different amplitudes. Like if one is for, let us say, electric field, and the other is displacement of, let us say, electrons, then you have two variables. You might have more or less, but then now you want to have no forcing at the right hand side of the equation. So this set of equations is linear. Okay, set of algebraic, actually linear, not algebraic linear equations. So as long as right hand side is zero, you would have total solution zero, unless determinant is zero. So, but you want to have non-zero solutions with zero right hand side. So this means that the determinant of this set of linear equation must be zero. That the determinant of this A, but symbolically let us say Aij. Aij is constants of this linear set of equations. The determinant must be zero, and this condition exactly is exactly what gives you omega of k. So this is a general procedure when you do that. So we did this for Kelvin-Helmholtz. It was somewhat tricky because we needed to tailor as a solution in two ranges of the space. So it needed it was like go to Fourier space at some point. Linearize, actually write down your equation system of equation of motion. Actually, what we did, we had equation for upper part and lower part, and then we needed to tailor the two solutions here and there. So this thing here depends on what you have. Might be a little more steps. Might have a few more steps here. A few more steps, like we had a few more steps in the case of Kelvin-Helmholtz. But yeah, in general, this is a very standard approach. Whatever you do, whichever field you study, this is how you do it. But there is one small modification to it. So instead of writing down equation of motion, actually you can start from Euler-Lagrange equation. So raise your hand if you are fluent with Euler-Lagrange equation. You did have analytical mechanics, right?
Yeah.
And there was thing which was called Euler-Lagrange equation, right?
Yeah.
So yes, this is something which I guess you go into physical theory. Statisticians quite a lot like. Why they do like? Well, it depends. And sometimes it's not that easy. For instance, in the case of Kelvin Helmholtz, it was not very straightforward or easy. The reason is that in that case it was a little bit difficult to express energy. So for Euler-Lagrange approach, you need to have expressions for energy, kinetic and potential. Now, I am not going to do full introduction to analytical mechanics, but let us just go to the conclusion. So the conclusion, just to recap what you did. So I guess you forgot. You had it, but you forgot. So yes.
The equation that you mentioned was the one like the derivative of the Lagrange and
Yes,
the equals to the derivative sign there. Okay.
Yes, exactly.
Okay.
The thing is, suppose just a very brief like introduction. So suppose you have a system with 1 degree, a mechanical system with 1 degree of freedom. For instance, something like that. Let us say we have here a wheel, and then we have here like let us say a wedge here, and then we have here goes a rope, and here is a brick here, and then yeah, here we have also a small wheel. Okay, you can just keep it like that. You don't need to make it unnecessarily complicated. Okay, now here, what you can do, you can just express the total energy in terms of one single coordinate, like displacement of this guy over here, x. So this displacement of that guy is x. So if we displace it by x to left, then this will that part here will change by x. Becomes longer by x. Right, because this horizontal piece becomes shorter by x, so the hanging part, the inclined part becomes longer by x. So this small brick on the wedge becomes down by delta y. Let's y displacement or vertical displacement y is equal to x. If here we have alpha, x times cosine alpha. And then we have potential energy is given by potential energy of this thing here is mg and displacement x. But if potential is bigger than it is when it's up, also we have minus sign here because the bigger x is a smaller potential energy. Minus mg x cosine alpha. This is the potential energy. Then now the next step, we express the kinetic energy in terms of the time derivative of x. So time derivative of x is the speed of the wedge. So we can immediately write down kinetic energy of the wedge. This is m, and this is m small. Mx dot square, and then we need to add here the kinetic energy of the brick over there. And now we can calculate this in two parts, which is horizontal and vertical part, 1/2. So horizontal speed of the horizontal component of the velocity of the brick is going to be now the wedge moves to left with speed x dot. X dot is the speed of wedge, but horizontal velocity of the brick relative to the wedge is x dot times cosine alpha, because it goes down by x x, which means that horizontal projection x times cosine alpha. So we need to subtract here minus x times cosine alpha, which is the related horizontal velocity of a brick on related to the wedge. So in ground frame, this difference is what is the horizontal velocity or square this, and yeah, we plot here actually small mass, and then we need to add a vertical one, and vertical one is just x dot cosine alpha squared. X dot square cosine square alpha. Oh no, not cosine. And now I made a mistake. This is not cosine, but this is sinus. This guy over here is sinus. Sinus alpha. Here we have still cosine alpha, but we need to fix with the potential energy. Sinus alpha. And here it goes also as sinus square alpha. Now I think I got it fixed, because a vertical component is x dot sinus alpha, horizontal is x dot cosine alpha. And so, here is our expression. And then we can simplify it. Now x dot goes before the braces, x dot squared divided by 2, and then goes m plus m, and then goes 1 minus 2 cosine alpha plus cosine square alpha plus sinus square alpha, which equals now x dot square divided by 2 and m plus 2m and 1 minus cosine alpha. And here is our expression for kinetic energy. And then total energy, which is sum of them, is conserved. So T plus V is constant. And this is now x mg minus xmg cosine sinus alpha. Plus x dot square divided by 2m plus 2m 1 minus cosine alpha. And now we take derivative. Find the derivative of it, the d over dt, and then we have here minus x dot mg cosine alpha plus x dot x double dot. If I take like using chain rule to take derivative of x dot squared, is x dot x double dot. 2 goes away and remains the same thing what we had already, m plus 2m 1 minus cosine alpha and closed. And from here now it's already, this is all 0. And from here, because energy is constant, so derivative is 0. And from here, it's now already very easy to express the acceleration x double dot. Now, this works because we have only 1 degree of freedom. In this case, the displacement, the state of the system, we were able to describe using with only a single quantity, which is that x over here. So if we fix x, already the position of the brick over there is also defined. So this is a single degree of freedom. But you cannot repeat this thing if you have more than 1 degree of freedom, because in that case you would have 2 variables, like let us say you have 2 degrees of freedom. For instance, we have let us say we have a V, and then we have here spring connecting them, and then everything is on ground. And so each of them, let us say these are cylindrical wheels, each of them has mass m, and we have stiffness k of the spring. And then we ask, for instance, what is the oscillation period here? Now here it won't work, and everything can roll. And yeah, actually, you can make it a little bit more funny. Like let us say this is sphere, and this is cylinder. Like to make it less obvious. And now we have actually 2 degrees of freedom because we have displacement of one wheel and displacement of the other wheel, y. And now it is not so easy anymore because what we did, we wrote down energy conservation law and took derivative. But we will be getting only one equation, but you will be needing 2 here because you have 2 variables. And so this doesn't work. So what does work is, in that case, is a Lagrange approach. And now how to derive that Euler-Lagrange approach? Now, yeah, how I usually do it, I do it through quantum mechanics, actually, as a matter of fact. So Lagrangian approach basically states that this is like least action principle comes into play. So least action principle. Let us see if we have, you know, Fermat principle, right? That if you have optical waves coming from somewhere and going to somewhere, and we may have certain coefficient of refraction depending on the coordinates. Then the light goes through the shortest optical path. So how it comes into play, you can actually think in terms of wave equation of Huygens principle. That you start building wavefronts, and then you'll see which wavefront is reaching the first the destination, and this is where you have the light coming. But if you know, start tracing back, so wavefront actually goes according to lines which are perpendicular. So basically, by building Huygens wavefronts, you find out the shortest possible path. Can you feel it? That it's like I make a small circle over here, and then the next envelope is based on the small wavefronts over there, and this is envelope what is going on here, so that the envelope like tests all the possible directions, and this is the fastest line where it can go in the given time. So you feel that you have like a testing of all the options to arrive from the starting point to destination. And now if you go to quantum mechanics, then you know that particles are also waves. And but in that case, what you need to calculate is phase. So here we have the optical path is minimal. This also means that the phase is minimal because optical path is like L optical is now instead of that we can consider phase. So phase is integral of k dx, where k is k dr. K is the wave vector and dr is the displacement. So this is k dr is small displacement d phi, and you sum up over the given trajectory all the d phis, and then Let us continue, but I need to share screen again. All right, so because k is omega divided by k is omega divided by v. But v is c divided by n. So we obtain here k is n times omega divided by c, but omega is constant and c is constant. So this guy over here becomes omega divided by c and integral n dr. And so this is optical path basically. So you can see that optical path must, in order to phase phi be minimum, optical path is needed. And now we do the same thing for quantum mechanics. So if we do the same thing for quantum mechanics, then we have phase. Now the phase would be kx minus omega t. And now omega is not necessarily constant, let us say, then d phi equals k dx minus omega dt. But now if we multiply this everything by h bar, then I obtain h bar df d phi equals h bar k is momentum. Is momentum p times dx minus h bar omega is energy minus energy times dt. And now let us divide and multiply this by dt and bring dt before the braces, then we obtain p times v minus e dt. And so we introduce total phase divided by h bar, total phase multiplied by h bar as what we call action. Action S is integral h bar d phi on the one hand, on the other hand, it is now integral pv minus e and integral dt. But pv can be written as kinetic energy times 2. And so this thing over here becomes 2 times kinetic energy minus potential plus kinetic. And all together equals integral. Now what we call Lagrangian dt, where Lagrangian L equals t minus v. And here you are. This is what is called Lagrangian. And similarly to how do we have the Fermat principle in classical optics, then which comes from wave optics from the Huygens principle. And in the same way we have coming from quantum mechanics for classical particles statements that particle moves along trajectory which gives you the smallest action S. And action S is defined as LDT. Yes.
This one is the same method to get the brachistochrone.
Sorry?
The brachistochrone curve.
Brackets?
Brachistochrone. Like the path that is left time for a ball to fall.
Yeah.
The same.
You can try. You can do it. Now then. What does it actually mean? It means that we have how we optimize. It means that we have we consider so-called phase space where we have coordinate. Usually in Lagrangian dynamics, you use coordinates q and q dot. coordinate, general coordinate, but now you can have more than one. So it's like multi-dimensional space actually, and you have starting point somewhere and you have ending point. And then yes, the true trajectory is such a trajectory which has minimal action, least action breaks. And action is now action S is integral L, but L actually now depends on coordinates qi, qi dot, and in principle it can also depend on time t if you are non-stationary, and dt. And this must be minimal. Now, what is the use of it? The use of it is that before our statement, if you write this Newton equations of motion, they are related to Cartesian coordinates, which are perpendicular to each other. But here, the statement is unrelated to any coordinates that we have. So we did not use we just describe the system for a set of coordinates qi, but they don't need to be straight or they can be lengths of elements or whatever. So they are not necessarily Cartesian coordinates which are perpendicular to each other. So arbitrary parameters which can describe the state of a system. So it is a very generic formulation now. And so in this way, using this, you can now the next step would be to derive the differential equation from this least action principle. The thing is that now we consider a small perturbations of the trajectory. Let us say this is the true trajectory, but let us consider a small perturbation which goes at a small distance. So this here is a variation and delta of qi as a function of qi of t and q dot qi of t and respectively qi corresponding also qi derivative. So a path which is very close, a small perturbation over here. And so similarly to how you have a maximum minimum when a derivative is zero, here the variation of s must be zero. Delta s must be zero. On the one hand, on the other hand, we see how much this integral thing changes if we introduce small perturbation. So L comes as a function of qi dot t. So first, yes.
What is that? I mean, like the function, the Lagrangian is a function that like stays like leave. The action leave in a Hilbert state, right? Because it's a function, and like when we differentiate, like
it's like you take derivative in the Hilbert space. You can say that, yes.
But q are infinite. Right? No, sorry, delta.
Delta q. It's like delta q is a function itself, but a small function with very small magnitude. The magnitude of the function itself at any point of t. So q is a function of t. At any point of t, it is very small. Delta q is very small.
And this removes the problem of infinite degrees of freedom of the perturbation.
Right now, okay, maybe I'll reach to end and maybe things become clear. So, delta q is a very small change to the function q of t. So I assume that we have optimum at q of t as a function of t. And then we take small variation that now q of t goes instead of qi of t goes old qi of t plus small variation delta qi of t. That's what we are seeing. But that variation can be arbitrary. Arbitrary function. It doesn't need to have the same sign. It can cross to the other side or whatever. Doesn't matter which one. And then let us see what happens to the integral, how much will the integral change if we make such a variation. So integral change because the quantity on the integral changes. And if change of qi at any t is small, then we have like a change of L is because first we change qi and second we change qi dot. So first it goes term delta L over dqi and delta qi. And I write delta qi assumes it's a function of t. But then it can also come because qi dot changes. So then I have also dl over tqi dot and delta qi dot. And yeah, but if depending on L, nothing will change. L is like constant function of t. So that's the thing how much it will take. And everything integral is taken from the starting point to ending point. And here we assume that yeah, actually we sum over all the i's. Actually, we assume that because this like repeating indices, we sum over repeating indices. And now the next trick is that we have two terms. One depending on qi and the other is tqi dot, delta qi dot. The trick is now to take integrating parts, so the second term. So this thing term now becomes integral from a to b dl over dqi delta qi plus now minus, because if you take the derivative, so I swap the derivative to the other side, and we integrate by over t. So actually here, this guy here is a derivative of t and integrate over t. So we take time derivative here and swap over here. Time dt goes dt. Sorry, time derivatives. Time derivatives goes that. But if we do that, the sign goes opposite, right? So this becomes now minus the time derivative d over dt of dl over dqi dot. And now this will be also having delta qi and dt. And then we have still one last term, which is plus dl over dqi dot and dqi from a to b. But now the thing is actually we assume that the starting point and ending point must be equal. So delta qi at a is 0 at the initial moment of time. Sorry, t equal to 0. Yeah, at point A, at starting point A is 0, and the same is at point B. So actually, this guy over here goes away, because I assume that there is no variation at starting and ending point. It still needs to start from A and end up at B. So the last term goes away. And then let us see what we have. Then we have integral from A to B.
And it's like what is 0? It was like okay,
yeah.
Yeah.
And then yeah, it goes from A to B, and let us bring together delta qi goes before the braces. So dl over dqi minus d over dt of dl over dqi dot. And yeah, then braces will close, and then we have delta qi, but this is a function of t, and then dt, and this all must be 0. And now let us analyze what we have. First of all, we have here different i's and sum of all the i's. And then we have here something in the braces which is fixed, but the delta qi is a variation. It can be anything. And but this must be 0 for whatever variation we have. This whole expression must be 0 for whatever variation of coordinates tq of t we have. So we can have, for instance, variation. Let us suppose that this guy here is non-zero at a certain point of the trajectory. Let us say, go back to this figure over here, and let us say that at this point here, the thing over here, how we express it, something like f, for instance. Let us denote this f. Suppose here f is not 0. Then we can take variation, which looks like that. Variation which is 0, no variation or whatever along here, but here it goes. No, it's actually, it was bad choice of color. Let me take yellow. Yellow might not very good, but still. No variation along the trajectory, but here it goes like that over here. And then it doesn't matter what kind of f we have over the rest of the trajectory. If there is a single point where f is not 0, we can make the variation whatever we have, positive or negative, what we need, as long as there is f is not 0 at a single point of the trajectory. So in order for this expression to 0 for whatever point variation what we have, we need to have that f equal 0 everywhere. So we need to have f equal to 0. Okay, only if f is 0 everywhere, and then for any I and any time point of t, then our variation is 0 for whatever variation we have. And this is what is called variational calculus. Yes.
So the variation is like a test function. The variation is works like a test function.
A variation is a very small change in the function. So in differential calculations, you have dx is infinitely small change of x. Variation is the same thing, infinitely small change in the value of the function. So x is a single coordinate, but here, as you mentioned, it's a vector function, is a vector in Hilbert space. So a variation of a vector, delta f, variation of f, is a small change in the vector in Hilbert space. Okay?
Yeah.
All right. So is it now more clear? And that's why, from where comes the Euler-Lagrange equation. So that finally we have, we could have taken here also just copy paste this over there. Let us see if we can make it. Okay, and this guy over here must be 0. No, why doesn't that? Still one more. And this thing here is 0. And this is the Euler-Lagrange equation. And yeah, you can write it also in this form that d over dt d over dt of dl over dqi dot equals dl over dqi. And you need to keep in mind that our L was equal to t minus v. But actually, that t minus v, keep in mind, the t minus v was assuming So T equals P times V, which is valid only Q dot, P times Q dot. Q dot. This is only classical mechanics, only classical mechanics. So if you go to, let us say, relativity, then you have completely different Lagrangian. But as soon as you have Lagrangian, you're done. So, so you can write your equation of motion immediately. And now let us go back to what we have at hand. So we wanted to derive equation for the Rayleigh-Taylor stability. And let us make use of the Lagrangian approach. We could have done it differently also, but just I wanted to show you one more way to do it. Well, you can say that it is not strictly turbulence, but then again, it is something which is very universal. And if you haven't met it before, I think it's very useful to know how it is done. So let us go now to turbulence. And now we have here row 1 and we have row 2. And then we learned that if the flow starts moving, initially B was everywhere 0. And so vorticity was 0, curl of B is 0 and will remain 0 because full-time derivative, Lagrangian derivative of curl of B is 0, and if it was 0 at the beginning, it will remain 0. And then we have also, yeah, we can also actually we arrived from here. We did it before, actually, as a matter of fact, but we can take a curl of the Navier-Stokes without dissipation for small perturbations. So actually, that curl of these is perhaps not that much needed, but let us write dV over dt times rho plus now nabla V plus gradient of P is 0. But then for small perturbations, this goes away because this is small times small, which is very small. So we neglect that gross term. And then we take curl of from here. If we take curl, the divergence, sorry, not curl, but divergence. We take from here divergence. And then we obtain, because divergence of V is 0, we obtain nabla square P, or Laplacian of P is 0. And then this means that if we look for a perturbation of this shape in a sinusoidal way along X, let us say here is this is given as xi displacement as a function of X. Xi is vertical displacement here. As a function of X in the form that xi is certain xi not xi as a function of wave vector k eikx. Then also all the perturbations have the same dependence on X, sinusoidal. In particular, also pressure as a function of y and x is equal to P pressure as a function of y times e to the power of ikx. And then because Laplacian is 0, and so we obtain d square p over dy square minus k square p equal to 0, from why I obtain that if we write characteristic equation for p, say like p equals kappa e to the power of look in the form of kappa y, then we obtain times certain amplitude p naught. Then I obtain from the conditions that the Laplacian is 0, we obtain that kappa square equals to k square. So that kappa equals plus minus k. So that's the solution. will be P equals P naught E plus minus kappa and Y like that. All right, and so also the perturbation must be like that, and the same goes, of course, then for displacement psi. Everything must depend in the same way. The function dependence must be the same for both velocities and coordinates. And now, let us. The next step would be now for us to write potential energy and kinetic energy, keeping all this here in mind. So we know that, well, if we have a perturbation evolving at the interface, there was no perturbation before, so it should be quite obvious that it must decay to the either side of the interface. So if Y is vertical, and so this must go to P naught E minus kappa and modulus of Y. So it must decay to either sides of interface. And now we are going to express kinetic and potential energies. So we still have that interface. And here is displacement of particles. Psi in principle is actually a vector. It can be, let's assume it is a vector. But what matters here actually is, maybe better, we assume this is scalar, so y is horizontal. Eta is horizontal displacement. And now psi as a function of coordinates x and y must be then certain amplitude psi naught E I k x minus k eta, well, sorry, y, k y. And that's it, I guess. But psi naught itself is a function of time. So this might start evolving in time. And so that velocity, x component of velocity dx is equal to psi dot equals psi naught dot, and still the same thing, ai k x minus ky. It goes away exponentially in y and sinusoidal in x. And what about Vy? We have divergence is 0. So dvx over dx plus dvy over dy must be 0 on the one hand. On the other hand, we have this expression over here. So dv from here we have first we plug in dvx over dx, which is now taking derivatives over x is the same as multiplying by ik. So this is ik and vx, and then we have taking derivative over dy, but we have exponential over that. So taking derivative over y is the same as multiplying by minus k and y and signum y. And all this must be 0. Yeah, and vy, I forgot here. Let me add here vy. and all must be 0. And from here we can obtain that Vy, k goes away. Now why did I have a y modulus? There is no y modulus. When I take derivative of y modulus, it is signum y just. I don't know why I wrote that y modulus, but there is no y modulus. So Vy from here now equals at least Vy modulus. So I actually care about modulus, so I can forget about those k's. Y modulus is equal to I modulus times Vx modulus. So by modulus, Vy and Vx are equal because the I modulus is unity. So basically, it is just enough to calculate kinetic energy related to the x directional motion, and we can multiply it by a factor of 2 to obtain full kinetic energy. Okay? Because Px and Vy are equal by amplitude, oscillation amplitude at any point of the liquid. And so now the kinetic energy is equal to up in upper semi-space ρ1 integral ρ1 divided by 2 times 2 times 2 because I count both x and y directional Vx square and d cube r volume element. And then this thing now becomes ρ1/2 c psi naught dot squared. And then we have integral both in x and y direction. What this now in y direction, actually now I need to keep in mind that this is actually Vx is a real valued thing, so it's a real part of this exponential thing. So this becomes equal to integral e minus k y from 0 to infinity, this along y direction dy, and multiplied by integral from over the total volume what we have at hand of a cosine square k kx dx dz. Now a cosine square average value is 1/2, so this becomes 1/2 of the total surface area A. Average value of cosine square times total area. And so then, but this is only the one part of the kinetic energy of the liquid above. And this becomes ρ1 divided by 2. No, the two went away. How did I keep it? But that 2 went away, but we have another factor 2 appearing. So that 2 went away, but we have that 2 coming. So we have ρ1 over 2 psi naught dot squared and A. And that's it. But full kinetic energy, now of course we don't need to do the same for the liquid beneath, so you just can add the same thing with ρ2. So total kinetic energy is ρ1 plus ρ2 divided by 2 psi naught dot squared times A. This is the kinetic energy over here. All right, and half the work is done because now we still need to have potential energy. Now everything clear more or less so far? I have been writing and writing and writing, but I don't know how you have been following. Artur, what about you?
One question about
I can't hear you. Maybe my phone is off.
I hope so. Can you hear me?
Let me see. If you try to just a moment. I can try to see if we have now saying something.
Does this work?
Yeah, your sound seems working, but my audio probably is not working.
The seconds before there were 2 outputs. There is Taltech AV.
Let us try now staying.
Yeah. Can you hear this?
Still now. Now let me go back. I think that was correct. Now.
No.
Let me switch over. Maybe. No, this is. And now try saying again.
Does it work?
Still no. Let me try to. No. Oh yeah, I know. I can also from here. I think I can troubleshoot to something like that. Maybe sometimes this works. I think it's related to Zoom. Test like if I.
Yeah. Maybe.
Yeah.
Does it work?
Yeah. No, I think now it started working. Yeah.
Okay. Yes.
Yeah. So.
Yeah. So in the integrals for T1, we have the integral from 0 to infinity of e to the minus ky. Doesn't that mean there's a
Oh, yeah, I
factor?
forgot. Okay, yeah, thank you very much. Actually,
Okay.
when I'm taking integral over y, I should have, but I forgot here k. So this is divided by k. All right.
Yeah,
Everything fine now?
that makes sense.
Yeah, thank you very much. This is my mistake. Anything else? Fine.
Yeah, except the video is now not working in Zoom.
Mhm.
So I can't see the classroom, just the screen.
The video was not working.
Yeah, the video, so I can't see you anymore.
Okay. Let me see. But you did see before.
Yes.
Okay.
Yeah, now it's back again.
Yeah. Okay. All right. Now, then let us continue. Now, guys in the room, what about you? Yeah, are you fine?
I actually have the same question
Yeah.
about the.
Okay. So now let us keep this in mind, and we can maybe we can just copy this over. I copy this over. Now this is kinetic energy. T. Now, what about potential energy? So we have still the same profile like that here, and then average value of, again, we need to integrate potential energy. First, potential energy due to gravity, V1. Now, if we find the potential energy by small columns. So initially, the column was, so we can imagine like taking column from here and moving to here, right? Maybe we can just say that the potential energy is on perturbed surface
was reference was everything was flat. So now we have somewhere above and somewhere below. So this part now, if we take reference potential as this flat part here, then we can see if you agree with what I write or not. But I am saying that the potential energy is going to be density difference now. And so if we have here rho 1 and here we have rho 2. So if it goes up, then and rho 2 is, let us say, bigger than rho 1, and then we have a positive potential energy. Rho 2 minus rho 1 is the density difference multiplied by the volume to get the mass, dx dx dz, and then multiply by the height of it, multiplied by psi. The height, xi, not cosine kx, basically, is the height. And then multiplied by the height of the center of mass, which is psi naught divided by 2 cosine kx. Integral like that. And we are still missing g. So we have a mass, which is rho dx dz, and psi cosine kx. This is dm. dm, let us say, something like that. And here we have dy, the change, delta, not dy, but delta y. And delta y times g gives you the change of potential energy. Agreed? And then we first need to integrate this. And dx dz gives us again the area. So it will be the area multiplied by rho 2 minus rho 1. And xi naught squared. And divided by 2. And cosine square kx gives us another 1/2. So altogether divided by 4, and g, and yeah, that's it, I think. No, I am still missing actually again the same thing that I integrate over dxy. Did I integrate dx dz? No, I don't need to integrate over y. So there is no integration over y. So now k appearing as before. I integrate only over the surface, right? So previously I needed to also, even to calculate kinetic energy, I needed to integrate over volume, but now I integrate only over the interface. Because potential energy takes place, a change of potential energy takes place only on the interface. And now we can also actually express, if we want, capillary energy, the change of surface area. So V2 is now, if we have here certain small angle alpha, then what happens with the surface area? It becomes bigger, right? So surface area here is proportional to the dl. So if this is here dl and here we have dx, then dl equals dx divided by cosine alpha. It's approximately equal, but alpha is very small because we have perturbations. And this is equal to dx multiplied by 1 minus cosine alpha, minus alpha squared divided by 2, minus alpha plus alpha squared divided by 2. Agreed? For small angles, cosine is 1 minus alpha squared divided by 2, but we divide by cosine, so minus becomes plus if I go to the numerator. Taylor expansion, first term, a second term actually. And Enrico, all fine? No? Oh, yeah, which Enrico? All right, so we can, because of that, that is constant part. If we integrate dx, it is just the total length. But this is by how much it changes. So we just keep only that part over there. So V2 is then equal to Yeah, but alpha is a derivative, basically. It is a tangent alpha is a derivative of the function. So it will be equal to dx psi over dx. This is alpha squared, 1/2 from factors r, and then sigma to obtain surface energy. And then we integrate over dx and dz. And xi square, again, this is the same as multiplying by a wave vector squared. So this becomes now k squared. Cosine goes to square, gives average 1/2 again, 1/4 sigma, and surface area A. And xi naught squared. Without dot squared. And all together, the total now Lagrange equals rho 1 plus rho 2 I hope I didn't make mistake. Let me check here over here. The seems okay. I'm not sure. Maybe I have some a mistake with vectors too, but we'll see if we have or not. Maybe not. And now Lagrangian is now just based on the final result to decide if I made a mistake or not. And if I made, then I need to find it. Rho 1 plus rho 2 divided by 2. Maybe not. Maybe everything is fine. Psi naught squared A divided by K minus potential. And potential is A rho 2 minus rho 1 psi naught squared divided by 4 times G and minus V2, which is now K square 1/4 sigma A psi naught squared. Something like that. And now the Lagrange equation for that. And now here, what are our Lagrange variables? Actually, we have only one parameter psi naught. We have many. What do you think? Seemingly one, but actually psi is a Fourier component. So actually, we have many. We have different wave vectors. Psi naught is actually a dependent on wave vector k, right? So this is infinitely many degrees of freedom because our wave vector can have many wave vector k. And now dl over dx psi dot and time derivative. So we have d over dt of dl over dx psi naught dot is going to be rho 1 plus rho 2 psi naught double dot. So if I take derivative over psi naught dot, then we have xi naught dot. Oh, sorry. No, I made a mistake. We have said the outstanding time derivative was it's just like that. And A divided by K. And this guy here must be equal to dl over dx psi naught, which is now minus minus A row 2 minus row 1 psi not over 2 G minus K square divided by 2 sigma A and psi not. And then actually the second derivative time over dt gives a second derivative of psi. So it's psi and not double derivative over time. We can see that we have here actually harmonic oscillator basically for psi naught. So let me copy now this to the next screen. Copy everything, but okay, let me try as I can. Yeah, and what did not get copied was 2 dots over here. And now now let us write here omega square. Omega square equals factor which is on right hand side divided factor which is on left hand side. So we have A goes away. We have row 2 minus row 1 divided by row 2 plus row 1 times G. And now what about factor of 2? Something is fishy with those 2s. I think still there is some mistake with those 2s which shouldn't be here. We can go back and see why we made mistake. And then minus plus K, and we have here also K because we have K over here. So this goes as K over that. And then we have K cubed coming to the next term. K cubed sigma A psi, no psi, sorry. No A goes away. And divided by row 1 plus row 2. And somehow factor 2. But those 2s shouldn't be here. So maybe we can go back and see why we made mistake by a factor of 2. Potential energy is where did it start? Okay, it started here. Potential energy is rho v square divided by 2. Vector 2 counts here that we have both x and y components. Those 2 goes away. And but then 1/2 comes from the fact that we have cosine square averaged. And we are looking only for a factor of 2. And so overall, it should have only a factor of 1/2 because that 1/2 and that 1/2 cancel away. And seemingly 1/2. And when we add up, we have row 1 plus row 2. Now let us see on next page what about those things over there. Potential energies. Cosine square gives 1/2. minimum fine mistake with calculation of energies. Okay, why I don't like it? Because um, if we take rho 1 equal to 0, see, factor 2 needs to be actually in the denominator, not at the. So maybe it's very. Not factor 2 needs to be in the nominator and not in the denominator, because in that case, when for the shallow water, for deep water waves, we have this special relationship. If rho 1 equal to 0, then we need to have rho 2 divided by rho 2 gives us 1. And then we have answer is g times k. So actually, that factor of 2 doesn't is wrong. That shouldn't be here. And so if rho 1 equal to 0, yeah, it's still wrong. Factor of 2. Okay, let it be. Let it be. I think it's easier to assume that we made mistake with the kinetic energy, because we had when we had kinetic energy, then that would fix those mistakes of the capillary waves and of the deep water waves. T is dx. So we kind of need to have factor 4 and not 2. Okay, let us. I'm trying to find a mistake later. So actually, correct answer should be some ways a mistake with the factors. Correct answer. Omega square equals rho 2 minus rho 1 divided by rho 2 plus rho 1. G times k and plus k cubed sigma divided by rho 1 plus rho 2. Somewhere that the factors 2 went wrong, but this is the correct answer. And now let us have a look here. So if rho 2 is bigger than rho 1, then omega is always real. And on the other hand, if rho 2 is smaller than rho 1, then the first term is negative. And now, for instance, if we have like negligible surface tension, so omega becomes omega square becomes negative, so omega becomes complex, and we have instability. So this is called Rayleigh-Taylor instability. If omega square is smaller than 0, then we have Rayleigh. And now this is a thing which is a very wide application in cloud physics. You probably have seen very nice photos of supernova remnants, like the Eta Carina and such kind of figures. Have you seen them? Very nice figures. We grab nebula, for instance. Okay.
what you see over here is actually Rayleigh-Taylor instability in action. So all those nice filaments are now maybe I need to. I'm not sure if Arthur can see my screen. I see it's a full screen, not only a whiteboard. Now you should see, right? So here, all these filamental structure, this is a very deep nonlinear action of Rayleigh-Taylor instability. And so basically, you have explosion, you have deep matter, dense matter is pushing away matter from there, and if you go to poor moving frame, it like happens that we have dense matter fluid above sparse fluid, and so it starts going evolving into filaments. How the Rayleigh-Taylor instability starts evolving is something like that. You have first you have flat surface, then you have a certain unstable mode, and then it starts evolving, like it goes deep like that. Oh, well, it's not very correct because surface areas must be equal. This surface area must be equal to that surface area here. And so a nonlinear stage of Rayleigh-Taylor instability is quite complicated to analyze. And we can also Google maybe some photos of nonlinear Rayleigh-Taylor. Yeah, lot of nice pictures. Maybe here. Yeah, it's just Wikipedia paper. Wikipedia article over here. So it starts, simple blob starts going, and then later on, actually, as you can see here, what will be happening? You have like combined Rayleigh-Taylor and Kelvin-Helmholtz because over here now, yeah. Oops. Let me copy this and put to the whiteboard, and I can make markings over there. Yeah, so here you have fluid going down, and here is going up. Yellow is going up, and blue is going down. And then you have here shear, right? And you have here now developing on the background of Rayleigh-Taylor, you have developing now also Rayleigh-Taylor instability vortices. And then it goes like more complicated things. And this, I guess, is from numerical simulations. Real life is even more complicated. So as you saw from the Grave Nebula photo. Also, this is something which there is a fusion project. Which now probably is most popular is the so-called tokamak project, like ITER, International Thermonuclear whatever. But then there are different competing projects for fusion, controlled fusion, and one of them is like compressing so-called liners, like spherical shells, which are filled with deuterium and tritium into towards center using lasers. Here you have a shell, and inside you have deuterium and tritium mixture. And then you direct here laser beams on all the sides.
And the idea is that it starts evaporating somewhere. If you direct here laser light, outer cells are evaporating, create additional pressure, and it all will start collapsing into single point. Like you hope it to go like that. But then again, if you go to cohomologic frame, it appears that you'll have Rayleigh-Taylor instability involving, and that's not what we'll be having. You'll be having like instabilities evolving. It's something like if you take like a bottle of Coke, let us say empty point, and start compressing it, it will not go homogeneously, but it will like make such various folds and irregular scratch shape will appear. So the same thing. This is a very nice problem, very nice idea to have a fusion reaction, but Rayleigh-Taylor instability is what spoils the things. So you need to basically try to have as smooth as initial, as homogeneous as possible initial profile. So yeah, there is Rayleigh-Taylor, but if the initial profile is very smooth, maybe it will not evolve too fast, and you can compress it to a certain extent. But still, this is Rayleigh-Taylor is here what makes easy success at least. And yeah, so there is also I don't know if you have seen, but there is like a very nice lamp actually. I think it's called plasma rocket. I can also Google it. And see here, I think video would be best. I don't know if this is the best figure, but let us try the first one. I think let us mute it. But no, this is not it. This is completely wrong thing. Completely wrong. This one. This one is probably the right one. Aha, this is some Russian website. AliExpress, for Russia. Chinese for Russia. Well, let us see if we can also show us some video. Seems as if, but yeah. So what happens here? You have below you have lamp lighting, and then you have like a wax and a fluid which has density quite close to that of the wax. And then now why doesn't it play? What is the matter? Oh, okay, we can just see here on some pictures. So these are different stages of the evolution. So you have at the bottom first, if the wax is cold, then it sinks into bottom. And then you have lamp, which is heating, and this becomes, once it's heated, it becomes less dense. And then you have a slow, very slowly evolving Rayleigh-Taylor instability, slowly evolving. You also remember that increment had a difference of rows divided by the sum of rows. Row 1 minus row 2 divided by row 1 plus row 2. And then Rayleigh-Taylor instability evolves, and then those blobs go up. And here, actually, the parameters are such that actually surface tension is also quite important. So when we had a look on those crab nebula things, then there was like negligible surface tension because it's very big scale, and surface tension had to such a small scale.
That's why all those filaments were very small. But now, if surface tension comes into play and the Rayleigh-Taylor instability is weak in a sense that ρ1 minus ρ2 divided by ρ1 plus ρ2 is small, then surface tension can suppress the Rayleigh-Taylor instability for quite a while. Let us have a look at the formula what we have. The formula what we have is ρ1 minus ρ2 divided by ρ1 plus ρ2 gk k cubed sigma divided by ρ1 plus ρ2. We can actually instability condition write down here. So instability is ρ1 plus ρ2 is here and there. So we have ρ1 minus ρ2 times gk1 Gaussian array must be okay. Let's write it the other way around. ρ2 minus ρ1 must be bigger than the next term. This must be bigger than k squared sigma divided that's it, k squared sigma, and then which means that k must be smaller than square root of ρ2 minus ρ1 times g divided by k. K squared. No, k. No, divided by sigma. And then we see that we have if ρ2 minus ρ1 is small, then the critical value of k becomes smaller and smaller and smaller if we decrease sigma 1 minus sigma 2, which means that it is stable for small wavelengths, big case, until k becomes equal to that, and for bigger scales, for bigger wavelengths, it becomes unstable. And so, so it depends on the ratio of a difference of rho divided by sigma. And if we go back now to the picture what we had before, then here that critical scale wavelength is already around the size of the plasma rocket. So diameter. So only the it's like values are chosen so that not very small instability wall, but only the biggest ones do that. And okay, it's just then how it goes on. The bubbles go up, then they cool, and then they sink down, and then for a while you have circulation over that. And it's actually quite a nice thing. Not saying that you necessarily need to order it from AliExpress, but but actually it's a very nice story. We can make also a screenshot from here and put also to our sheet. All right, now we have talked quite a lot about instabilities. And I think we more or less need to stop here. Although actually it's quite interesting topic is still to speak a little bit about waves on deep water, so to say. So if we again look back what we had at hand, the dispersion relationship. And as I said, that let us put ρ1 equal to 0. So we shouldn't have this term here. We shouldn't have this thing here, and then it is correct. And if we put now ρ1 equal to 0, then we have omega square equals now ρ1 is 0, ρ2 is just rho. Rho divided by rho is 1. We have a g times k plus k cube sigma divided by rho. And just if we have no surface tension, it's just k, gk. So it means that we have dispersion, meaning that phase speed, v phase, is square root of gk divided by k. Phase speed is omega divided by k. And this equals to now
square root of g divided by k. On the other hand, growth speed is d omega over dk. Is now comes 1/2 square root of g divided by k. And so next lecture actually we can start a little bit to talk about what does it mean when we have now a growth speed 2 times smaller than phase speed. This is actually quite interesting things come up. For instance, if boat travels on deep water, then a wave pattern below. Basically, something like that. We have here. Let's make the boat a little bit smaller. Small boat and a big wave. Boat is here, and then it creates wave behind it. So each line of constant phase of phase will be something like that. But mostly the waves what you see are these things here, like these are the most intense parts of the waves. And this is one of them. Next one is followed by another like train of waves. Something like that. And here is magical number angle which is formed. I don't remember exactly. Again, something like 36 degrees or something like that. Again, next time I can calculate what it is. So if you have you noticed behind boat or ship such kind of train of waves? You have? Not so. Yeah, you can actually open Google Maps and look somewhere where you have a lot of speedboats. Sometimes you can see nice wave pattern behind them. All right. Now, last time you did not have homework. Let us have this time. And since we talked about instabilities, and then we have still one more. This is also the guy Sir Lord Rayleigh was very active in such kind of things, and this is stability is also named by him, but also a French guy, Rayleigh plateau instability. What is this about? If you can make experiments at home. You take a tap, open, water starts going. Here is a tap. Now water starts going, and you take a very narrow stream. Okay, what happens? At certain point, this guy here breaks down into droplets. And this happens because of Rayleigh plateau instability. So Rayleigh plateau instability is if you take a cylinder of water and then consider how it will evolve. So here again we have you assume here you have a perturbation of this shape, cylindrically symmetric, and you can try deriving here the instability increment. So you assume now actually what is easy, one thing is not quite easy to know, the other thing is quite difficult to do. So if you want to make full and proper analysis, then you would need to have consider here cylindrical coordinates. And so what is water doing? So water particles move from here to here. So we have velocity component from right to left, and here we have from left to right. And then they go to here. But because we assume small perturbations, and mostly it is this horizontal motion. As long as wavelength is big as compared to the diameter. So if lambda is much bigger than b, then motion mostly horizontal. And you in kinetic energy calculation, you basically can neglect vertical motion of these water bodies. On the other hand, if this is no longer the case, then you would need to do proper 2D calculation, cylindrical coordinates. And then you have something like Bessel functions, maybe, who knows, it's more complicated. So I am not asking to do the complicated thing. I am asking you to calculate gamma as a function of k, instability exponent, as you see in this approximation. When instability is only give rise to only horizontal motion of water bodies. Is it clear? So I think it's easiest to do using the energy, using the Lagrangian approach. You have potential energy of surface tension. And T is kinetic energy of horizontal motion. So it was a simplified calculation with only horizontal motion. And then when you write the Lagrange equation, you should obtain gamma. So if you do proper analysis, gamma of k, what happens then? So you should have something like that. The smaller the k, the bigger gamma. The gamma as a function of k should be something like that. You have a big k, you have a bigger the k, you have this gamma goes was k. But then this is as long as we neglect vertical motion. But if we include vertical motion, this will start making it slower. And as a matter of fact, very small perturbations become stable because you make perturbation and so total surface area will grow. And then actually you will have something like that. And so I am asking you to calculate this part over here. Calculate here. Here. Because that part over there is more complicated to calculate, and it requires cylindrical coordinates and 2D motion. But what happens in reality is what starts evolving is the most stable mode. So this K naught, which is the most unstable one, this is what you'll see. Usually, if you have like this kind of thing, that gamma in stability exponent is a function of k, then during a given initial perturbations, the other will not manage to evolve into really seeable thing, but the fastest one is the first which you start noticing. So in reality, if that's why that cylinder will evolve into nice sinusoidal graph in reality, because evolves as the most unstable mode with the optimal k, which is a few times of the diameter of the cylinder. So is it task clear, more or less? Do you think you can do it? Hopefully. It'll try. All right. Now, let me ask before we go away. So
This time, this was not so much related, a little less extent related to turbulence. So I'm asking if you're okay with that, because I kind of myself feel that it's nice to know and you like useful things. But what is your opinion about it? So, did you like what we learned today, or would we rather stick to more to turbulence?
I really like this part, like
Okay.
the Lagrange stuff and the
Yeah.
variation calculus.
Arthur, what about you? Yeah.
I like to see it. I have seen the instabilities themselves before, but not the Lagrangian approach to evaluating them. So I like that.
Okay, all right, good. So just because I'm like slightly deviating what is in the study program, so that's why I'm asking if you're okay with that. So we go back to the study program during the next lecture. So don't worry. But I think still we start next time. I'll be showing you how to calculate the wave pattern below the load, because I think it's quite a fun thing to have. And then we go to now next thing is actually a Kolmogorov turbulence. All right, so thank you for attending, and until next time.
See you next week. Bye.
Until next week.